Hi everyone. Here we're going to be talking about evaluating machine learning models, the accuracy, precision, recall, and F1 score metrics. So there are multiple evaluation metrics, each of which has its own distinct strengths and approaches. And the best metric will be based on your particular goals, what you're trying to maximize, what you're trying to achieve. The common metrics include accuracy, various measures related to confusion matrix, actually of which accuracy is one, and these are usually used for classification problems, these two here, accuracy and confusion matrix. And there's the R squared, so you should be familiar with that when you studied regression, and that's for regression. And area under the curve, also other measures for when we're looking into when we also have a quantitative target variable. So these are more the regression kinds of model evaluations. These are the classification ones, and I'm going to be focused on these ones here in the set of lectures. So we can actually take the approach both for accuracy and all the other kinds of metrics, like recall and precision, from the notion of a confusion matrix. And we need to first understand that this refers to a binary classification. So that's when you have two classes, 1 and 0. And the 1 is a positive class, meaning that the feature of interest is there, and then 0, it's not there. And there are essentially only 4 possible outcomes in this case. You have, when you apply a model, the model can identify the feature that should be negative, or that is the lack of a feature, a 0 in this case. We're going to call this negative correctly. So if we have a negative case and then the model predicts it correctly, we call that a true negative. And if the model doesn't, that means it predicts a positive when it should be negative, then we call that a false positive. It's positive, but it's false. That is, it should have been marked as negative. Another possibility is on the positive side. So the model predicts that the thing is a negative, but it's actually positive. So we have a false negative. And then also potential to be, the model predicts it as positive when in fact it is it is positive, and that's a true positive. And we'll go over some examples of that to facilitate the understanding of this. Note that in statistics, this identifying a false positive is also called a type 1 error, and a false negative is the type 2 error. So these are the two errors, and these are the two correct predictions, but we're making a distinction between whether it's predicting correctly when it's positive and when it's negative. And this can be important when we go over some of the examples, especially, for example, when you're dealing with disease detection. So disease means if it's 1, you have the disease. If it's 0, you don't have the disease. So it makes a difference if the model is predicting true negatives or false positives, or true positives or false negatives. So the rate of each of this makes a difference, and it's not just true or not true. So let's take an example here. Let's go more in detail here. Now we have some results from the some of the data that we had, and here we have an N of 450. And so let's keep with the example of detecting a disease. I think this will help us go over this. So suppose that you had a data set of let's say COVID-19 tests. And the COVID-19 test has, we need to know that there is we kind of names of people, and then we actually have the test results of that are true and the test results that are predicted. Okay, so let's say these are the true results and these are the predicted results. Now let's say a person in X had COVID, so this one, another person 2 did not have COVID, a person 3 had COVID, a person 4 did not have COVID. And then so those are the true values. And then you had an algorithm, or you had in this case a test, a COVID-19 test that took the blood sample from the person and said, oh, this person does have COVID, this person also has COVID, the third person also has COVID, the fourth person does not have COVID. So actually, the predicted test didn't get it right all the times, right? Not 100%. Actually, in one instance, it did not get it correctly. So this is what we're working with. Now, suppose we had 450 of these and not just 4. And there were 356 true negatives. That means the person did not have COVID and the test correctly said that the person did not have COVID. We had 51 false positives, meaning that the test said the person had COVID, but the person did not have COVID. That's a false positive. There's 5 true positives, means that the person did have COVID, like here, and the test predicted the person had COVID. And then there's 38 false negatives. So the test predicted, let's have another one, a false, but we don't have any false negatives here. The person did have COVID, but the test predicted not, 0. So that's a false negative. So every test instances is in exactly one box, or all the possible results. And then the idea here is that we have 4 different kinds of results, and we can combine these in different rates. So you can think about in each of them, for example, true negative rate. What's the true negative rate? Well, true negative rate is 356 divided by 450, right? What's the true positive rate? True positive rate is 5 out of 450. Now the thing is, it's going to depend also on how many of the instances you have in your data. So you got to be careful, consider that. How many false negatives? 38. How many false positives? 51. Now, the more formal measures that we use are the following. One is the accuracy, and accuracy is the proportion of the total number of correct predictions that were correct. So that's the true negative plus the true positive. True negative plus true positive, the proportion of the total number of correct predictions divided by everything that was predicted. And here you can calculate as wish, 356 plus 5, right? 356 plus 5 divided by all of these summed up. I don't have a calculator right here, but you can do it, and I wonder what you're going to see. Now the result is going to be what? It's going to be a fraction, right? So it's something like 0.63. I don't know if it's 0.63, but it's going to be between 0 and 1. And that's a basic measure of the goodness of the model, the accuracy of the model. However, we can have other measures that emphasize different things. This measures emphasizing everything. You can see that it includes everything on the denominator and 2 measures on the numerator. So it's putting everything there to be considered. Now, we have the classification error, which is just the opposite of the accuracy. It's 1 minus accuracy. So that's the fraction of all instances predicted incorrectly from the whole data. So you can kind of get, it's the the 1 minus of the accuracy. So it's kind of, they're related to each other directly. Now we have this important measure called recall. So recall, also called true positive rate or sensitivity, is the fraction of all positive instances predicted as positive. So here we're giving a focus to the positive, okay? And notice that the numerator is the true positives, and the denominator is the true positive, but also plus the false negative. So we're kind of emphasizing this area over here. If the true positive is high and the false negative is low, then we're going to get a high measure. But notice that this model is not considering the false positives, because we're just not so much concerned about false positives because it's focused on the true positives and the false negatives. Now, of course, if false negative is high, then the overall measure is low because high is in the denominator. So it's considering the false negative. And this may be important in disease testing cases. And it's good. Models with higher recall will identify more true positives, but also minimize the false negative. So good to determine how well a test can identify a disease when it's present. So if you really want to make sure that your model identifies a disease when it's present, you want to minimize the false negative. And here you're less concerned about false positive, because if a person gets a false positive, well, they're going to be more alert about the issue and take a precaution, even though it's a false positive. But if it's a false negative, that's really bad because the person goes out there and thinks that they don't have the disease when they actually do. So the recall brings up the false negative and the true positive, and it's used in medical context for this purpose. Now we also have the specificity or true negative rate, which emphasizes, as the name suggests, on this region here. So here is the fraction of all negative instances predicted as negative. Okay, so that's Tn, true negative, divided by true negative plus false positive. So it's kind of like the recall rate, but on the other side, on the negative. Here you're emphasizing the true negatives, and helps you minimize the false positive, because if your model has high false positive rate, then this measure is going to go, if this here goes up, the whole value goes down, right? Now we also have a measure of precision. So precision is fraction of positive predictions that are correct. So this is also focusing on the positive side, but it's highlighting these two dimensions here, considering these two here. So that's the true positive rate divided by the true positive rate plus the false positive rate. So this emphasizes that you want to predict the things, the positive predictions, okay? And the model, if the FP is low, you're going to have a high precision. If the FP is high, you're going to have a low precision. So that's what I mean by helps to minimize the false positive. Here there's a list of all the different combinations of the values you can have here over the rates, and you can see more on the link attached here. Oh, and also there's a last one, which is actually the F-score. And the F-score is a good thing because it combines both precision and recall into a single measure. Because usually there's a little bit of a difference between them, and there's a little bit of a trade-off if you want to increase recall, if you want to increase precision. And the F1 score kind of puts them two together. And the way it works is this, it's kind of a simple formula. You just multiply the precision times recall and divide it by the precision plus recall. And we do times 2 to make sure we have a number between 0 and 1. This multiplication of 2 does that. So a score of 1 indicates perfect precision and recall, and a score of 0 indicates either perfect precision and no recall, or perfect recall and no precision. So we want to, have the number closest to 1 possible. Very small precision or recall will lead to lower overall score. If you have a very small precision or very small recall, and we don't want that, we want high both, and that's the F score combines them two and helps with that. We can get the accuracy measure in Python from the KNN algorithm by using the test sets. So this KNN assumes that your model is already trained, and then we use the score function on the test set that was not used in the training. And then there are going to be a value between 0 and 1, so maybe depending on your how many K you used, maybe you get 0.53, which is not very good. It's not a very good model. It's kind of like half. So you want something higher than that, but the model, it is what it is. So you do want accuracy. Accuracy of 0.5 is not good. That's kind of like almost chance, almost like flipping a coin. So you want higher accuracy. You can also use the other measures we discussed, the precision score, recall score, and F1 score, which are the main ones we usually use in machine learning context. And the way to do that, for example, when we have the KNN algorithm, is we're going to predict, we're going to use the predict function from the KNN, but instead of just using a few numbers as we did in the previous example, we're going to use the whole X test data frame. Once again, we need to predict on the test data, not the trained data. We can't predict on the trained data because the trained data was used to build the model. And here we're just getting the results and putting it into a variable. And this is going to be just an array of values that are predicted. Now, remember, this here is a multi-classification. This is from the fruit data set. And from the fruit data set, we have multiple categories. 1, 2, 3, 4. 4 different types of fruits. And what we've been talking about is these are all binary, right? These are all binary. So it's just true, you got a true or you're not true. Now, you can expand the confusion matrix to multi-classification problem. And you do something like what we do with the dummy variables, right, in regression. So lemon, did it predict a lemon correctly? Did it predict a mandarin correctly? So we can turn each of them into a binary classification, but you got to think about that when we use these measures, because for each of these measures, you want to average out how all of the different fruits were categorized. Now, if you just have one, if it's just 1 or 0, the average won't really matter that much because it's just 1 or 0, and all of these precision and recall scores will follow the formulas I just went over. But now you have multiple different categories. So there's lemon positive or negative lemon. There's mandarin positive mandarin, negative mandarin. There's orange positive or negative orange. By negative orange, I mean 0. Orange, yes. 1 positive, orange, no. 0 negative. So you kind of, for you to test the model, you need to average out all of, for each categories, the results of each categories. So this is why there are different averages we can choose for the precision, recall, and F1 score of this specific KNN model here. And I will include a link of that for you to look into the different average. And I suggest you to try the different ones, the macro and the micro, as you do the exercise for this class. So in general, one important observation is that there's a trade-off usually between recall and precision. And there are recall-oriented machine learning tasks. So for example, as detection of diseases, as we were saying. So usually we want to make sure that if it's positive, we identify the positive, even if it means we identify more positives than exist. That is, we have lots of false positives, but at least we minimize the false negative. Now, also where situations where a human expert can filter out the false positives can be, we can use recall, and then also information extraction in legal discoveries. All of these situations in the recall, we minimize the false negative. So that means that maybe we can have greater false positives. Now, here the precision-oriented machine learning, it minimizes the false positive. So things like, so you ensure that you, if you classify something, if you identify something, then it's not a false positive, it is really there. So document classification may be a task for that, or search engine ranking and query suggestion, and various related tasks where it's a customer-facing tasks, and the idea here is that the user will remember the failures, so we want to avoid them. So we don't want to identify things or pages that the user says, oh, this is wrong, this is not the page that we were looking for. So you are minimizing the false positives in this context, and that's a precision-oriented approach. And there's usually a trade-off between the two, although we can kind of address that by using F1 score as well. And that's some of the evaluation metrics for machine learning. I'll see you all next time.